graphs here. So the first thing to notice is this b here is going to stand for theta, and we're going to swing b up from 0 all the way to 2 pi. Generally speaking, our polar graphs are some sort of r, is a relation to theta. It's sort of a function of theta. So like r equals sine of theta, for example. The radius depends on theta. So as I swing out my angle theta, represented by this green dotted line, my r is going to be graphed by whatever the sine of that angle theta actually is. So let's turn on the r here. And we can see as for sine theta, my radius is increasing as I sweep my graph out all the way to 1, and then decreasing back to 0. And this happens from angles of 0 to pi, completes one full loop. And so if we're going to trace that loop, we're going to create a circle. We hit our maximum value at pi over 2 of our angle of 1, and then we make it back to a radius of 0 after pi. If we take a quick look at the graph of y just equals sine x, or you could imagine this being r equals sine theta, for our angle of 0, we start at 0. We sweep out and our radius is increasing all the way up to pi over 2, where we hit a maximum of 1, and then we are decreasing all the way back to 0 from pi. And so plotting a function r equals sine theta, as defined in polar, is going to create this exact effect from 0 to pi. And that's probably the most important initial idea to understand. The other thing to note is that our radius is in positive value all the way from 0 to pi. And so that means that my radius is going to be considered positive, and it will be plotted in the same direction as my angle. So if my angle is facing this way, then my radius is plotted in that same exact direction, however far in that direction it's supposed to be, which in this case is equal to exactly sine of theta. So our basic sine of theta, sine of 1 theta, or just sine theta, creates this circle on the domain 0 to pi, which corresponds to this piece of our graph, of the rectangular graph of sine theta. Notice after pi, we're going to end up with a negative radius. And we define negative radius in polar as just projecting backwards, or in the opposite direction that the angle theta is facing. So for the section of the graph from pi to 2 pi, we're actually going to see the same exact sort of shape as we see from 0 to pi. It's just going to project this backwards. And so what actually happens is if I change, or if I keep going here, see how my angle theta is pointing into quadrant 3, but because that makes a negative r value, right? Sine is negative in quadrant 3. My radius is considered negative and projects backwards compared to the direction the angle is facing. And it does this the entire time sine is negative, or sine of theta is negative, which is in quadrants 3 and quadrants 4. So as I sweep through quadrant 3 and quadrant 4, I hit my maximum value of 1, or really we should think about it as negative 1, just projected backwards, giving me that same value of 1, and then we complete this full circle. So on the domain of 0 to 2 pi, I complete one full circle, and then because I'm projecting my radius backwards, I have this symmetry where I'm creating a second full circle right on top of the first one. What will happen if I create, or if I include an absolute value here, is that now my radius will never be negative. So if I made sine of x the absolute value of sine of x, well, now that just flips my negative portion of the graph back to positive, so sine is always positive. So we should expect this to plot in the same direction that my angle is facing. So the initial part is the same, 0 to pi, but now the radius is going to be positive in quadrants 3 and quadrants 4. So I'm going to plot out in the same direction my angle is facing, and we're going to see that second circle. Let me just change somewhere in here. I have to put absolute value. Maybe right here. Let's see if that worked. No. Vector 1, actual r and theta. Vector 2. Yeah, so I don't know. Somewhere in here I'd have to change something to make this radius actually do maybe an absolute value here. And here. I don't know. I don't seem to be getting the radius to go in the direction I want. Oh, that's not great. Yeah. Well, let's actually refresh this page here. Okay. So anyways, here's our vectors. Somehow I'd have to go in here and dig out to make it actually work. It's a little complicated. But if I just make this part the absolute value, we can see that a second circle is plotted there because it's going to be a positive r, and it's going to go in the same direction as this green direction of the angle. So that's really the basics. If you can sort of know and accept what sine theta is a circle, when it's just sine theta, it's two circles on top of themselves. But if it were absolute values, then it's sort of the mirror image because we just go all the way around again. Then that's basically all you know to be able to reason through virtually everything to do with the flower petal shapes. And again, here's absolute value compared to regular rectangularly. So now let's think about if we increase the a value, so like sine of 2 theta, for example, we end up with 1, 2, 3, 4 petals. And so what's happening here is that if I take my angle and sweep it out, since it's 2 theta, everything's now happening twice as fast. So here's an example. I can graph y equals sine of 2x. Notice how in the time it normally would take me to complete one cycle, I actually complete 2 full cycles. Or in the time it takes me to go from 0 to pi, where I'm always positive, that now actually occurs from 0 to pi over 2. So I'm getting twice as many cycles. As far as the polar is going to do, or is concerned, that means I'm going to complete that circle much faster. So it's going to happen just in quadrant 1 instead of taking from quadrant 1 and quadrant 2 to complete a circle, like here. It takes quadrant 1, quadrant 2 to complete one full circle. When I double and take sine of 2 theta, now it completes a full circle in one quadrant. But now it doesn't exactly look like a circle because it's all been smushed into one quadrant. So it creates this sort of flower petal shape because we sort of smush in here. Then we are projecting our angle into quadrant 2, right? That's where our angle theta is. But notice that after pi over 2, since we're doubling it, we're actually going negative already because that's the equivalent of being after pi. So as I sweep my angle out, I'm going to project in the opposite direction here of my angle theta. And so we're going to project out, complete this second petal in the opposite direction here, get to pi. And so from 0 to pi, I've completed 2 circles. Normally it would take me 0 to 2 pi if it was just sine of theta, but I'm going twice as fast. So now I've completed 2 circles, or 2 petals, I should say, in the time it should have taken me to complete just 1 petal. Now that I'm in quadrant 3, well, on my sine of 2 theta graph, I'm back to a positive radius. So I'm going to project in the exact same direction that angle theta is facing here. So here we go out in the same direction, create our third petal, bringing us to quadrant 4. And quadrant 1, 2, 3, 4 here. Notice that quadrant 4 is negative, so we're going to expect our radius to project in the opposite direction of our angle. So that's going to fill us out in quadrant 2, and we get this beautiful symmetry that creates a petal, 4 petals for us. Now in this case, we're going to get the same exact shape if we do the absolute value of r equals sine of theta, or sine of 2 theta, with the only difference being this time that, let me just turn this off because it doesn't really match. Now we're just going 1, 2, 3, 4 in terms of quadrants, because the radius is always going in the same direction as theta is. 1, 2, 3, 4. It's never going in the opposite direction. So if I throw absolute value of this, I'm always in the same direction. Up to 1, back to 0. Up to 1, back to 0. Up to 1, back to 0. So on this graph, every time I get to this sort of right about here-ish, that's my maximum value, a radius of 1 here. And then we come back towards 0, and then back out to 1, and back to 0, and all the way around. And that's absolute value. If we take the absolute value off, it just changes the order. And we project in the opposite quadrant. And so these even A values have this sort of symmetry so that they project in the opposite direction. So if I go with like A equal 4, now I end up with 8 petals, because if I had sine of 4 theta, or 4x, compared to sine of just x, notice that I get 1, 2, 3, 4, 5, 6, 7, 8 max and minimum values, up to the max, back down to the min, in the time it takes me normally to go 1 full max and then min. Because everything's happening 4 times as fast. So instead of doing 1 max and 1 min, 2 full things in 2 pi, now 4 times as fast, I do 1, 2, 3, 4, 1, 2, 3, 4, a total of 8 in 2 pi. And that's our sort of where we're getting these 8 petals from, because if I drag my angle theta, I get petal number 1, 2, 3, 4, 5, 6, 7, 8 full cycles by the time this angle makes it all the way around. And then there's this order that the petals are graphed. We start positive, right? Sine starts positive, so our first petal gets graphed normally. We might expect our second petal to be right here, but it's actually going to be the one opposite that because the radius is negative. So we get our second petal graphed opposite. Now, since we're back to positive, right, we go positive, negative, back to positive. So this chunk's positive, so we're going to plot our petal in the same positive direction. Our next petal is going to go opposite. You might think it would be here, but it goes opposite, so it's going to end up over here. And then we get the same direction, opposite direction, same direction, opposite direction. Notice this one's opposite to this. We close out. And so that's our petal order and how we can sort of figure it out. So it's just about how many cycles out and back and out and back and out and back, and we're either going in the positive or negative direction. Again, throw an absolute value on here. Everything's going to be positive, 1 positive, 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 positive. So all this is going to do is take our graph, and it's going to change the order and make the petals all go out and then back in, and out and back in, just in the very direction that the radius is sweeping out. And so all of our even petals will kind of look and follow this same pattern. So another thing to think about is maybe our odd numbers. So if I had A equals 3 sine of 3 theta, let's do that here. You can see we do 1, 2, 3 loops per pi. And then we do 1, 2, 3, or 4, 5, 6 loops in 2 pi. So you might expect 6 petals, but we don't actually get 6 petals because of sort of how the symmetry of this works. So if I pull this back and if I take off absolute value, my first petal is positive, so we go out in that same direction. My second petal is negative, so we have our positive piece, then we go to our negative piece. So that's going to go opposite. So opposite direction of this petal that you might expect here is going to get graphed in the downward direction. Then we complete this piece and we go back to positive. And so we're going to get a petal in the same direction. And voila, we've completed 0 to pi. So we've completed our first 3 petals. And that sort of compares to our regular graph. We've completed 1 full thing. Now, based on the symmetry here, I might expect my 4th petal to be right here, but we're now negative. So in this sine of 3x, from pi to whatever's here, we would end up with a negative radius. So that's going to project us right back onto the petal we already graphed. So let me turn this radius back on. As I sweep right through here, I'm projecting right back onto a petal I already graphed, so I don't actually get anything new. And then we complete that. So that's our fourth petal, but it's on top of itself. Now we're back to positive R value for our fifth petal, meaning that this is going to graph right on top of this petal that we just graphed a moment ago right here, because we're at pi over 2, but going in the negative direction. So I sweep out and I graph right on top of that same petal. Then I get to my last petal, and again, it's negative on this last piece to 2 pi, and so it goes in the backwards and right on top of itself again. And so this causes us to only get 3 petals. There's actually sort of 6, but they're getting pushed right on top of each other based on symmetry, just like they did for when A was 1. So this means if we take the absolute value, all of those petals are going to get revealed because now they project in the same direction as the angle. Nothing should ever be backwards, and this is what it would be if it weren't absolute value. But here we go. It projects in the same direction as the angle, and that reveals all 6 petals. It's only when we don't have this absolute value that this petal here gets projected onto here, this petal projected to here, and this petal projected to here, giving us only 1, 2, 3 petals. A problem that we don't really see when A is equal to 2, because the negative petals are projected just right back on top of where the other ones are, or opposite to where they are, as we run this, right? Now this is absolute value. But this is sort of, we go positive, and then we have this negative, then we have this positive, so the 2 positives sort of are opposite to each other, and then the 2 negatives are sort of opposites to each other. So they kind of fill in the blanks there, and you would see that here. Like we have a positive, then a negative, then a positive, then a negative, then a positive, and then this negative gets another negative to be opposite to it, so it fills that in. Then this is a positive, and then this one's got its negative to fill it in. So sort of the way the graph, what is this, 4 theta, sine of 4x works, this positive, this positive, this positive, this positive sort of fill in every 1, 2, 3, 4, but that ends up being 1, 3, 5, and 7. So you get petal 1, 3, 5, 7 filled in from the positive direction, and then the other ones just end up getting filled in negative. And so it all kind of just works out really nice. If we try like A equal 5, you only get 5 petals, because here we go, let's turn this back on. Same direction, opposite direction, same direction, opposite direction, same direction, and we've completed our full cycle. However, the petal that would be here, we're going to end up with a negative. So we're going to get onto the petal we already graphed. Petal that would be here, if we had a negative, well, we're back to positive, so this petal is just going to get looped over again. And then this one's negative, so I get looped back to here. And so that's just sort of the symmetry with these odd ones. And that's where we end up. Okay, so you can play around with that, but that's really the idea. It all came from simply this. One circle gets created, and then we have a second circle on top of itself, and messing with all these symmetries and kind of comparing to these graphs, you can reason through everything. Other cases to consider. So what if we have like a fractional value in for A? So let's do a nice simple one like 0.5. And so let's go down to A equals 0.5, and we'll scroll this back. A equals 0.5. Now if we compare this, let's see where we have 0.5. Notice how in the time it would normally take us to complete the positive and the negative petal, we actually only complete the positive direction petal. So we should expect that for a full rotation of 2 pi, my r should be in the same exact direction as my angle. And so as I sweep my angle out from 0 to 2 pi, notice that my radius is in the same direction, same direction, same direction, same direction, same direction. I'm never going backwards. Boom, 2 pi. So this whole time, my r is positive because it takes me that whole thing. It's this same piece of the graph, but just elongated. And so it's always positive. And we get this shape that we get right here because let's think about it. It takes us all the way, we're increasing our r, all the way until pi when we get 1. So here we go. We are increasing our r all the way to pi as an angle where we get an r of 1. But since it's in the direction of pi, it's at this sort of rectangular -1. But in polar, it's just 1, right? There is no negative in the left direction for polar. And then once we hit this maximum value of an r of 1 at pi, our r's are going to decrease all the way back to 0 as we continue sweeping. So we're decrease, 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 decrease. And the fact that we start at 0, increasing this whole time, increasing, boom, there's our maximum r at pi, increase, increase, or sorry, decrease, 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 and done. So that is this right here. We've covered the max and back. But before we get something that repeats itself, we're actually going to have to do our negative portion. So if I increase this to 4 pi, my domain, now when I keep sweeping beyond 2 pi, sine of a half of that is going to be negative because we're cutting the value in half. So that's like taking sine of pi in quadrant 3, sort of, once we sort of refactor. So now my r should project in the opposite direction of my angle theta, and we'll get this beautiful symmetry. Look, there's our maximum value, which is at this value 3 pi cosine -1. My angle's at 3 pi. I've gone around once and then another pi. And my r is projecting -1, so 1 in the opposite direction of my angle. And then we're decreasing, 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 and boom, complete the rotation. And so this should really apply as long as like I pick a number for a that has like some nice symmetry. I could pick like 0.25, and we should expect sort of the same thing. With 0.25, let's try it on this graph. Notice that it takes me all the way from 0 to 4 pi to complete my positive portion of the graph. So the portion that normally takes 0 to pi, since I'm taking 1/4 of my angle, is now going to take from 0 to 4 pi to complete. So I'm going to be positive the entire time, meaning my r is going to be in the same direction from 0 to pi. I should expect my max value at 2 pi of 1. So when I go to graph this, I should expect a maximum here right about when I make it all the way around once. So let's check it out. R is increasing, R is increasing, R is increasing, R is increasing, and boom, maximum value. My radius is 1 at 2 pi. This entire time my radius is going to decrease back to 0, the pole, but it's still going to be positive. So I should get some sort of symmetry as it decreases back to 0. And that's just the positive part of my graph. This entire time, I'll do it again. My radius r is in the same direction as my angle. Boom. So there we go. Now if I wanted to complete the cycle and get my negative portion of the graph, I'm going to have to go from 4 pi to 8 pi. And on this entire piece, I'm going to be negative. So I'm going to do this exact same thing. I'm going to go increase, 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 increase out to 1, and then decrease, decrease to 0. But instead of going in the same direction of my angle and following this path, it's just going to go opposite and follow an opposite path. So if I'll increase this to 8 pi, and I'll drag. And look, there we go. Same exact idea, but instead of being quadrant 1, I'm opposite in quadrant 3. Quadrant 2 is now 4, etc. Boom, there's my max. This has got to be, what is this now? 6 pi? My angle, yep, my angle's projecting at 6 pi. I've gone around 3 times now. And my r is negative, so it goes backwards. Now we decrease and complete our cycle by 8 pi, creating this nice shape. So even though the graph is really complex, you can reason through and sort of figure it out. Like you should be able to figure out that like, oh, okay, well, I know I'm going to be increasing to a max at 2 pi, And so if I just sort of drag out, I should expect to hit 1 after 1 full cycle, and I should be increasing this whole time, so I should spiral out to it. And then whatever we did to spiral out to it, we're going to copy that to spiral in. So we're going to get the mirror image as we keep going. Boom. And then because now we're going to be negative, we can expect to do the opposite as we go around again. And so that's about as much as I'd like you to understand there. You can mess with this as long as we pick a rational value of A. We should eventually be able to complete this. So if I pick like, say, what's a good rational value? Like 9/5. So I get 1.8. Seems like a little bit of an odd number. And so I'll get some interesting overlap here. But because this is a rational value, this will eventually sync up with itself over some period. So if I, what was this? 9/5, 1.8. So this should be cyclic over some period. You could calculate that out, but I don't feel like doing it this moment. Kind of looks like it's cyclic over 5 pi. So it takes me 5 pi to start repeating myself. Let's see if we can see that on the graph. So we go 1 pi, 2 pi, 3 pi, 4 pi, and 5 pi. So now, based on the fact that this sort of matches right up at 5 pi, I should be copying over my stuff I've already drawn, and I am. And that's a little advanced, but I think it's kind of an interesting fact that you can get these kind of shapes with rational numbers. However, if I picked something irrational, I would expect this to never repeat itself. And I'll leave that to you to think about a little bit, but this will never link properly up. So I can just sort of go around and around and around and around and around and around, and you say, oh, maybe it's just not enough. If I did like 80 pi, and I just let this run, you're like, oh, maybe it'll go, but it won't. It's pretty cool looking. You're like, well, maybe it just hadn't gone enough yet. But if I do like 800 pi, and if I zoom in a little so you can see the difference, because it's going to get kind of close. Sort of tiling in, you'll kind of notice things are still changing, things are still changing, things are still changing. And I mean, at this point, we've basically filled in our graph, but that can be sort of accounted for if we zoom in a little more, and you'll be like, okay, and what if I said 8,000 pi? I press play, and it's like, zoop, look at this, filling in, filling in, filling in. And it's getting kind of trippy. I mean, at some point, Desmos loses the ability to actually handle graphing this stuff. But if you kind of zoom in here, you can see that this isn't really ever going to match up. And that's because this is an irrational number. If I did square root 2x, right, I challenge you, square root 2x, I challenge you to find some here where on this graph where this actually cycles up with a pi. And it just won't. So kind of an interesting fact. But that's probably a little extra. What else? The last thing I'll have you look at is sort of the effect of adding a constant. Or actually, no, that's probably enough for this video. We're going to call it good there. Or we're going to just do the constant. Take a moment. So say I put a +1 here. Okay. What's going to happen? So for our basic circle, this should be pretty simple. Let's get this back to 2 pi. You should expect the radius to start at 1. And now it's going to go out to 2. And then it's going to come back to 1. And so this might not be 100% intuitive, but the reason this kind of happens is because your r is now going to be 0 only when, let's do an equivalent here, sine x +1, turn that on. We just shifted our midline up. So now we go out to a max radius of 2, and we come back to a minimum radius of 0, and that's going to happen every 3 pi over 2. And so we go starting at a radius of 1, our new midline, we're going to go out to a max radius of 2, back down to a minimum of 0, and then back to our midline of 1. Midline, max, midline, min, 0, midline, starting point. So there's one full cycle over 2 pi. So you just got to think a little bit, and you can kind of reason through anything here. Don't pay attention to the vector. That wasn't sort of calibrated. Okay, if I had more cycles, I don't think there should be anything new here. Let's take a look. Yep, we just go round and round and keep doing the same thing. Although I think if we put an absolute value here, or this part, we might expect it to look a little bit different. So there we go. So now sign is net or negative, but that's probably more to think about. So we start at a midline of 1, and let's just put it here so you can sort of get the visualization from that. Right, now we're going from a midline of 1 to max of 2, back to 1, back to 2, back to 1, back to 2. So here we are starting at 1, going out to 2, back to 1, back out to 2, back down to 1, and just repeat the process. So it's all about thinking. We just want to think. We want to think about our radius. We want to think about what's this doing? How does it compare to this graph and what we know about what sine does and over the different intervals? How does a multiplier affect that? So if I make a 2, interesting. If I make 2, right, and it's the absolute value still, that just makes it happen way more frequently. So now that same sort of behavior we had with 1, we now get twice as much, and this is with absolute value. Draw it out, and if we get rid of the absolute value, then we might expect a little something different. So that's kind of neat. We're starting at 1, going out to a maximum radius of 2, coming back to a minimum of 1, or sorry, midline of 1, if I take this absolute value off, then back down to 0, so I've got to hit my pole. From getting to 0, I'm going to go increase all the way out to 2. So I'm going to go increase first to 1, then to 2, then back to 1, then back to 0, and then repeat. And you could do it with more pedals. You just never know. So here we go, sine of 4x. It's just going to happen way more often. So here we go. We get some more pedals. But you'll notice that we've got 0s and 1s happening not exactly where you'd think. And so this looks kind of rotated. It's kind of neat. If I increase, I kind of rotate and do weird things. So you can play around with it. But the idea here is not to memorize every single thing. It's sort of just to understand what's happening. How does it relate to the graph of sine? How does the angle and negative r values create symmetry? So yeah, hopefully you enjoyed the video and found it informative. Ooh, and as an Easter egg, let's say, if you draw a picture of a cow on the top of your test near where your name is, I will give you plus 1% if you watch this whole thing. So let's see, cow for extra credit. Draw me something nice. Look at these cows. All right, hope you enjoyed the video. Thanks for watching.